Hello everyone. Today we will be beginning our discussion on college algebra by starting with the pre-algebra review. The first step in the pre-algebra review is the review on real numbers. Before we get into real numbers, we must first start at the bottom with natural numbers. So, what is a natural number? Well, if you think about numbers you count with, such as if you want to count milk at a store, you will start with 1, then you go 2, 3, 4, and 5. So, what's the characteristics of all of these numbers? Well, they are positive and they have no decimals. And that's the characteristics of natural numbers. So, for example, 17, 1,000, 121 are all natural numbers. The size of the number does not matter. All that matters is that it's positive and has no decimal. 17, 1,000, 121 meet those characteristics, so thus they are natural. Moving on from natural numbers, we have whole numbers. Whole numbers are extremely similar to natural numbers, as they are all natural numbers plus 0. So we take, for example, 0 as a whole number, but also 17, 100, 1,000, and 121 are also whole numbers. Past whole numbers, we reach integers. Integers is where we bring in negative numbers to the talk. So if we take negative 3, negative 2, negative 1, they are integers. But again, 0, 1, 2, and 3 are also integers. Integers must be positive, 0, or negative and have no decimal. Again, though, they are not dependent upon the size. So negative 1,000, negative 121 are integers. 0 is an integer, and 1,000, 121 is an integer. Past integers, we begin to talk about numbers with decimals, which are rational numbers. The textbook definition of a rational number is an integer over an integer. If two integers can be expressed in this form, then it is a rational number. For example, 1 divided by 10 is rational, 1 divided by 3 is rational. But remember, integers can be positive or negative. So again, negative 1 over 10 is also rational, negative 1 over 3 is also rational. Rational numbers can be expressed as fractions or decimals. There are two rules though for if a decimal is a rational number. The decimal must either end, such as 0.1. This decimal ends at 0 at the 10th place of 1, so thus it is rational. Another example is for non-ending numbers such as 0.33 repeating. This repeating sign above means that the 3's continue on forever, and this makes it a rational number. Without the repeating pattern, it would not be rational. If we take these two examples I showed, we can also express them as a fraction. 0.1 is equivalent to 1 over 10, and 0.33 repeating is equivalent to 1 over 3. So, even with expressing rational numbers as decimals, the original definition of integer over integer is still valid. What are some examples of non-rational numbers though? Well, if we take just 0.17914 and just have this go on forever with random numbers behind it, this is not rational. It's not rational because the number does not end and does not repeat, so thus it cannot be expressed as an integer over an integer. So what are these numbers called that are not rational? Well, if we move on to the next, we have irrational numbers. The only definition for an irrational number is a number that's just not rational. So thus, if a number cannot be expressed as an int over an int, is irrational. So we have the previous example of 0.17914 going on forever as an irrational number, but some more examples are pi and the square root of 2. Pi is approximately equal to 3.14, and the square root of 2 is approximately equal to 1.41. As you can see, there's many more decimals that go on past these numbers, and those are never ending. You cannot express pi or the square root of 2 as a fraction of the form int over int, so thus they are irrational numbers. Once we have the rational and irrational numbers counted for, we can then define real numbers. A real number is any rational or irrational number. If a number is not rational or irrational, then it is not real, but if it is rational or irrational, it's a real number. After discussing real numbers, we can now move on to orders of operation. If you remember from pre-algebra, you will remember the saying PEMDAS. I will write it here to the right, but again, I typically would like to write it on the left, like this. So why on this left example do I have the MD and AS written together? Well, I have these two letters written together because they are actually on the same level. This might be confusing at first, so let's start with an example. If we have 2 divided by 2 times 10, you might be tempted to do the 2 times 10 first, because in PEMDAS, M comes before D, so thus you would think I do multiplication first. But if we use my drawing on the left, we see multiplication and division on the same level of each other, so we decide which one to do first, left to right. So we do not do 2 times 10 first, we do 2 divided by 2 first, which is 1, times 10, which is 10. The same is true for addition and subtraction. If we do 2 minus 2 plus 10, again, you might be tempted to do the 2 plus 10 first, since addition comes before subtraction in PEMDAS. But since addition and subtraction are on the same level, we have to do it left to right. So we end up doing 2 minus 2, which is 0, plus 10 is 10. So after discussing that, we will go through with what PEMDAS means. We have P is the parentheses, which are denoted by 2 brackets. You do anything inside the parentheses first. Exponents are denoted as a real number raised to another real number, and we do that second. And then finally, we follow it with multiplication and division on the same level, denoted by a dot or an X, division dot denoted by a bar with 2 dots. And then lastly, we do addition and subtraction on the same level, such as addition with a plus, subtraction with a minus. Now we can move on to an example. So if we take 7 minus 5 times 2 plus 2 squared divided by 4. Well, first we must start with what is inside the parentheses. Inside the parentheses we have subtraction and multiplication. From PEMDAS, we do multiplication first, so we will have 7 minus 10 plus 2 squared divided by 4. Now we still have in the parentheses 7 minus 10, so we must continue. We do 7 minus 10, and we have negative 3 plus 2 squared divided by 4. Next, we have an addition, an exponent, and an addition. So from PEMDAS, we do the exponent first. We do 2 squared, which is equal to 4. So we have negative 3 plus 4 divided by 4. Lastly, we have addition and division. From PEMDAS again, division comes before addition. So we will do that first, and we will do 4 divided by 4, which is 1. And we will get negative 3 plus 1. Lastly, we will solve this addition problem, which is equal to negative 2. We will move on now to the last example that we were doing in this video, and that will be 3 squared times 2 plus 5 plus 7 minus 1. Again, we must start with in the parentheses. In the parentheses, we have an exponent, multiplication, and addition, so we start with the exponent. So we will get 9 times 2 plus 5 plus 7 minus 1. In the parentheses again, we have multiplication and addition. So we start with multiplication, and we get 18 plus 5 plus 7 minus 1. Finally, we have addition in the parentheses, so we get 23 plus 7 minus 1. Now, all we have left is addition and subtraction, so we move from left to right. We have 23 plus 7 on the left, so we will get 30 minus 1. And then once we do 30 minus 1, we will get 29. The last topic we will be discussing in this video is algebraic expressions. Algebraic expressions are when we get to bring variables, aka letters, into math. So, for example, we'll take 5x. 5 is called a constant. It is always 5 in the expression no matter what. However, x is the variable. The variable can be any real number. So you could set x equal to 2, x equal to 1, x equal to 3, x equal to 4. When we have an expression such as this, 5x, this is equivalent to 5 times x. So if we say we want to let x equals 3, this would be 5 times 3, 15. With algebraic expressions, sometimes you'll have more than one variable. For example, if we have 5x plus 2y plus 10x minus y plus 7. Now this looks like a lot at first, but if we deal with it slowly, you'll see that it's pretty simple to deal with. You might be asked, you want to simplify this. Well, what do you want to do? You might have also heard the term combine like terms. So what exactly does that mean? Well, when combining like terms, we want to see the variable and the degree on the variable, which is the exponent. If a term has the same variable and the same exponent on the variable, then it is a like term and we can combine it. So as we see here, 5x and 10x both have an x with an exponent of 1, so thus they can be combined. Y, 2y, and a negative y, again, both have a variable of y and an exponent of 1, so they can be combined. You just combine these like terms with simple arithmetic. So if we have a positive 5x plus a positive 10x, that would give us 15x. A positive 2y minus a y would give us a y. And finally, we have 7. As you can see in this expression, there are no like variables for 7, so we have just 7. But take, for example, if there was a plus 10 in this expression, 7 and 10 would be like terms since they have no exponent, so thus you would do 7 plus 10, 17. The last example we will look at in this video is 27h plus 30k plus 10m plus 5m plus 7m plus 3h. Again, this looks very long and complicated, but if we just go slow, one at a time, it's not that bad. We start with the h. We have h with an exponent of 1 for 27, and we have h with an exponent of 1 for 3. So that means we will do a 27h plus a 3h and get 30h. Remember, we can do that because they are like terms. Next, if we move on to k, we see we have a 30k here with an exponent, with a variable of k with an exponent of 1. And we see we have no other k's in the expression, so that means we cannot combine the 30k with anything. So that just simplifies down again to 30k. Finally, with the m's, if we look, we have m, and m. All three of these m's are the same variable, and they have the same exponent, so thus they can be combined. So if we do 10 plus 5 plus 7, we get plus 22m. And this would be the simplified expression. That will be all for this video. Thank you for watching, and come back next time as we will continue our pre-algebra review.